So we've been looking at limits going to infinity, looking at the end behaviors of graphs. We've been looking at asymptotes, horizontal and vertical, and we've been looking at equations and looking at those limits as they go to infinity. So I want to do some more examples with limits going to infinity and giving you tricks of how to solve those if we get an indeterminate form. Okay, so let's look at an example. And let's say that we have the limit as x is approaching infinity of the square root. And underneath the square root, we have this rational expression, which is 8x squared minus 3. That piece is in the numerator, all over 2x squared plus x. So if we took the limit here and we go in and we plug in infinity wherever we see an x and kind of analyze to ourselves what is going on, notice that plugging in x here, so 8 times taking a huge number that's going to infinity and squaring it is huge, minus a 3. So to me, that's going to say, well, this would be kind of like the square root. My numerator is technically going off to infinity. And then if I look at my denominator and I put in 2 times infinity squared plus infinity. So it's something that's growing and growing off to also infinity. And so we get this infinity over infinity and the square root of that. This is an indeterminate form. This doesn't tell us anything. We have to go back and we need to manipulate this. So we don't know if the limit exists or not and where it's going. And so let's go back and let's use rules of limits. So there was this rational power rule that says if we have the limit and we have the square root or nth root of something and what was underneath the limit exists, then we could rewrite it. So this is the same thing as the square root of the limit of this rational function 8x squared minus 3 all over 2x squared plus x. And so now when we go back in, still we have that problem, infinity over infinity. But we can use one of our tricks that we were doing yesterday, where we were multiplying by the fancy one, or another way to think of it is dividing every single term by the variable raised to the highest power in the denominator. And so if we look at our denominator, notice that is a x squared. So we're going to want to divide every single term in the numerator by x squared and every single term in the denominator by x squared. And so if we do this, we get the square root of this limit as x is approaching infinity. So distributing, okay, so 8x squared all over x squared. Notice our x squareds cancel and we're just left with an 8 there. Minus, so 3 times 1 over x squared. Well, that's 3 over x squared. All divided by, so let's distribute. So 2x squared all over x squared cancels, leaving us with 2 plus, and then an x divided by x squared. So we can use rules of exponents and that would simplify down as 1 over x. So now when we take this limit, we're going to use the fact that we know that if a limit as x goes to infinity of 1 over x raised to some power n, where n is a positive integer, then this whole value goes to 0. So using this fact, we now can, when we look at this limit, as x goes to infinity of a constant, recall was just the constant itself. So that would be the 8 here. Minus, well, as x goes to infinity, 3 over infinity squared goes to 0. So this is minus 0 all over the limit as x goes to infinity of our denominator. Well, the limit as x goes to infinity be a constant is 2 plus the limit of 1 over x as x goes to infinity goes to 0. So plus 0. So now we can simplify this down and we get the square root of 8 over 2, which is the square root of 4, which is 2. So if we were to look at the graph of our function, y equals the square root of that rational piece, we would notice the graph is heading off to 2 as x goes to infinity. So the limit exists, it heads to 1 y value.
A quick question.
Mm-hmm.
Why did you choose the 1 over x squared to multiply for both the bottom and the top?
Right. So the trick is that we want to get things in this form of 1 over x, because if we can get it in that form and infinity, when the denominator is blowing up, that 1 over infinity is 0. So the trick is to look at your denominator of your rational function and always choose the variable raised to the highest power. And if we do that and multiply by that fancy 1 over that, every single term is either going to cancel out your variables or leave you an x in the denominator. And so we know when the limit as x goes to infinity and we have the x in the denominator, that piece goes to 0. So it will eliminate things that we couldn't deal with before. So that's the trick on that. The other way that we talked about it was if we thought about this as a rational function and where your horizontal asymptote would be. So remember, horizontal asymptotes had to deal with what was the degree of the numerator, what was the degree of the denominator. So another way to think about this is, well, those degrees were the same. You actually looked at the leading coefficient at the top, all divided by the leading coefficient of the bottom. And so by knowing that there is a horizontal asymptote there, I'd have we would have that was equal to 4. And then I have that square root of the 4. So the horizontal asymptote degrees are the same. Degree was the highest exponent in the numerator, highest exponent in the denominator. If they were the same, then it was the leading coefficient at the top, which is 8, all over the leading coefficient of the bottom, 2. And so using algebra, that would have given us 4. And so this would have said, okay, I know that I have an end behavior when x goes to infinity of 4, and now I'm going to take the square root of that, which I would also get back to. So there's 2 ways to look at it. This method of dividing by the variable raised to the highest power is sometimes beneficial and helpful to do. Does that answer your question, Tim?